Hey folks, this is the first of two videos on orbital motion. This is a big exercise in logic having to do with energy, and we'll start simple and we'll get more complicated as we go. We're going to review a lot of physics here. So orbits of satellites can be circular or elliptical. Circular orbits are simple and demonstrate energy and angular momentum concepts in a fairly straightforward way. So I'm going to cover that first, and then we're going to talk about some interesting things along the way. So because it's circular motion, it means that you have a constant value of r. The satellite is always the same distance away from the center of the planet, no matter where it is. And as we saw in the circular motion section of our forces unit, there's a constant speed as well. So having a constant value of r when in orbit means that you're going to have a constant speed. So that creates some simple things. Some conclusions that we can make. The kinetic energy of the satellite is also constant. And so that's easy to digest. The next one is going to be a little of a trip back to a memory that you actually probably don't have because it's an equation I only talked about once of little importance. Gravitational potential energy in space is written as negative big G, big M, little m over r. So let's talk about that after we decide that because it's based on the masses and r, it's also constant. I don't want to ramble too much about this equation, but it is a way to convey gravitational energy only in space. We use it in space because that's where masses are isolated from one another. They're not connected. There are very few other masses directly around them, and the force of gravity acts over a great distance. This equation has a maximum value of 0. If you take two masses and increase their distance apart until that distance apart is essentially infinity, you've arrived at 0 joules of gravitational potential energy. At all other smaller values of r, the value of gravitational potential energy is negative. And as r gets smaller, this fraction gets bigger. So as r gets smaller, there is less and less gravitational potential energy. You're getting a more and more negative number, which means your gravitational energy is decreasing. So this is the way we model potential energy in space, and we'll have to get used to it again for this. But kinetic and gravitational potential energy are constant, and that combines to say that mechanical energy is also constant. Okay, next up is angular momentum. The rotational inertia of this satellite is equal to its mass times r squared. That is therefore constant. And angular velocity, we said that there's constant r and constant v. Both of those variables are relating to angular velocity in one of our equations. So v over r is how we would convey angular velocity is also constant. And so the rotational inertia and the angular velocity are constant for this satellite in a circular orbit, and that combines to tell us that the angular momentum, I omega, is also constant. So circular orbits are kind of boring because nothing ever changes as long as there's a circular orbit. And that's why we also study elliptical orbits. They exhibit all of these properties of energy and momentum, but with changes. And so what we're going to do is we're going to take this elliptical orbit, we'll imagine the Earth revolving around the sun, and we're going to take this Earth from point A to point B. And so that means that we are going to travel in this direction around the sun. And what I want you to notice is as we go from point A to point B, that value of r is going to decrease. It's very large at this first point A. It's very small at that point B, and so it becomes a smaller and smaller values. So we do have constant masses, but the value of r decreases from A to B. And so we want to like look into what happens as a result of that. All right, so we're going to go kind of quick. First one is gravitational potential energy, negative G mm over r. Okay, well, I talked about it in the circular motion one, but if the value of r decreases, this fraction gets bigger, and so the gravitational potential energy gets more negative. So gravitational potential energy decreases. What I want you to remember is that when we use like UG equals mg delta y, it's the same result, that as things get closer together, their stored energy decreases. All right. Next one. This force of gravity acts between the two masses, and gravity is subject to Newton's third law, as is every force. So the net force on this system is always zero because it's just gravity, and there's a force of gravity on each object in opposite directions. So mechanical energy is constant. We don't explain that by the behavior, but we do say that the net force is zero because there's a gravity force on each one that are equal and opposite, that balance. Now that leads us to another conclusion. If mechanical energy is constant and gravitational potential energy decreases, then kinetic energy must increase. Now this is nothing really new. As gravitational potential energy decreases, kinetic energy is going to increase. Just like a ball falling to the floor, Earth is essentially falling kind of at the sun throughout this half of its rotation. So that relationship of mechanical energy is still at play. All right, so next one. Because the net force on this system is zero, the net torque on this system is also zero. So the angular momentum has to be constant. So equal and opposite forces exert equal and opposite torques. So technically speaking, the sun does revolve around a point. That point is within the sun. It's just not at the sun's center most of the time. So, or all the time. It moves a little bit. Anyway, so the center of mass of this system, there's a torque on both objects. It affects Earth a lot more than it does the sun. All right, so we know that as our fact, and then what we're also seeing is because that radius is decreasing, that rotational inertia decreases. Okay, that's because r is going down. So the two facts that we've kind of collected based on the behavior of the planet is that gravitational potential energy decreases and rotational inertia decreases. Well, the last thing we can say having to do with angular momentum is if we know that the angular momentum is constant and we know that the rotational inertia decreases, then the angular velocity must increase. So these last things, like item 3 here about kinetic energy and item 6 about angular velocity, those are like the final conclusions based on the behavior of the planet that you can't see happening in a diagram that's static, but you would see if you analyze the motion of planets around suns. That's all.